Let's start here. I'm just going to talk a little bit about the test format, kind of what to expect, right? Because when's the test? Yeah, next class, so Thursday. Both of those answers are correct. One of them's for the people that aren't sure what day of the week it is, and the other is for the people that are. That was a joke, because I'm often not sure what day of the week it is anymore either. So the first two questions are just domain questions. You're just finding the domain of a function and writing your answer in interval notation. Two questions where I ask you if the function is odd, even, and neither, and you have to support your answer algebraically. Means you're doing the proofy stuff that we did in the notes. Two questions, just whether something's a function or not. Four questions that are sum, difference, product, quotient, or composition of two functions. There's a big block of questions like that in the review. Right? Do you remember seeing that? Yeah. Two questions where I ask you to find the inverse. When I ask you to do that, I'll ask you to write your inverse in the same form as the function. So if you got a mapping diagram, your inverse should be a mapping diagram. If you got a graph, your inverse should be a graph. If you got an equation, your inverse should be an equation. Same directions as from the homework or whatever. One question where I ask you to verify that two functions are inverses. How do I do that?
Put them in each other.
Yeah, f of g of x and then g of f of x should both give us x. Yep. One question where I ask you to, or where I give you a parent function and enter a resultant function and to describe the transformation in words in the correct order. Everybody's okay with that? Okay. One question where I give you a parent function, ask you to perform a series of transformations to get to a new resultant function. So I might tell you to, shift left 7, and then stretch vertically by 5, and then reflect across the x-axis or something like that. And then give me the resultant function after doing those things. And then one question where I give you a parent function as a graph, and then the transformation, and ask you to use that information to draw the resultant function. So I think that was in the last two questions or something in the homework were like that. And I think there was something on the review like that too, right? It's been a long time since I looked at all these things in super depth, but I know that they're in there. Any questions about the format here or what to expect to see? Okay. Again, the hope is that really there's no surprise, right? That this helps narrow things down into just, we did a lot of stuff. What am I going to look for you to be able to do? Not everything. Here's the stuff that I am looking for, right? That's helpful, I hope. Do you guys have any homework or review questions or any other kind of like test formatty kind of questions or anything like that that you want to talk about here before we start in on chapter 2 things? I'm guessing by the opening of books that there's maybe some possibility of some yeses here. So I'm just going to kind of jog in place and let the people that are flipping pages frantically have a chance to find that without us all sitting here in uncomfortable silence. Now you just get to sit here with Mr. Kulik uncomfortably babbling and without really saying anything at all. But at least he's talking, so it doesn't feel weird that we're just sitting here silently, right? Because silence is sometimes more awkward than just somebody that won't shut up, even if they're not really saying anything. Tessa! From the review or the problems? The problems got to be. There weren't 48 problems in the review. I mean, there might have been, but they weren't numbered that way. All right, so 48 from the problem set. Okay. And did you need to do all of it, or are you just looking at part of it, or
Just like the last.
just E?
Yeah.
Great. So we're just going to find the inverse for this. So it's already written in a y equals notation, so all I'm going to do is go straight to getting the x by itself. So I'm going to start by adding 9 to both sides. And then I'm going to multiply both sides by x plus 4 to get rid of the fraction. And then I'm going to divide by y plus 9. And then subtract the 4 over. And now that the x is by itself, I can swap the variables and write it as an inverse function. Does that feel okay? Sometimes it is more complicated in your head. That's why we do the homework for practices, so you can see like, oh yeah. It's okay, make a mess out of the homework. Now's the time to get all the mistakes out of you, right? So you can get to the test that you got all the silly things out of the way, and it's like, okay, I got it now. Others. Yes, Katie.
For 37,
37B. Do I need a new page? Yup. That's okay. 37B. Okay. This says to state the domain and the range for this using proper interval notation. So the domain is just going to be the x values. So that's just 3, 5, and 10. And then the range would be just the y values. So that's just 2 and 4. Notice that I'm writing those with the set notation rather than an interval, since these are just specific values.
okay, so you can write them all in the same thing.
Yeah. Yep, that's okay. The way that's written is okay with me. Tessa. State the domain and the range for the relation. I guess that's just a mistake. Yeah, that just, oh boy, it did something there and it moved it on me. Try it undoing again. There we go. Yeah, it just must be a mistake. My apologies. Katie, you're happy though?
Yeah.
Yeah. Hopefully that was the kind of answer you're looking for, right?
Yes, I know.
Yeah, no problem. We didn't do a lot of examples where we used like the regular old set brackets as opposed to an interval. Allie.
For 56, like when you're like you have to use function composition.
Mm-hmm.
After you like plug in the numbers, I just like wasn't sure how to just go.
Yeah, do you care which way we do? F of G or G of F? It doesn't really matter, right? I'm just going to do the first way. And you're probably good with one of them, right? Like once you see it one way, it's probably pretty obvious what to do the other way, right?
Yeah.
Okay. What do we got here? Okay, so 3e, and then in place of the x, I'm going to write the natural log of x plus 5 over 3 minus 1. And then I have the plus 1. And then the minus 5 is down here. Does that all look okay to you? All right, let's start simplifying. I'm going to start in the exponent. The first thing I notice in the exponent is that there's no reason that those extra set of parentheses need to be there that I wrote, since there's no multiplication or division going on in front of the parenthesis. So that's going to allow me that the +1 and -1 can cancel out. And then I noticed that the natural log is log base e. So I have e to the log base e. Since the exponential and the log match, they can just cancel without having to do anything else. And that canceling is going to drop that exponent out of the exponent just like as it into a coefficient. And then the times 3 can cancel with the divides by 3. And the +5 can cancel with the -5. And we're at x, which is what we're looking for. You're welcome. This is the step that is probably the one that's a little fuzzy, right? Is remembering that like log base b cancels exponent base b and vice versa, and then that action drops whatever was inside the function just onto the main level. So it's no longer an exponent, or it's no longer locked inside of a logarithm. It just tumbles out. That's all that's left. Anybody else? Happy to do more? Yes.
Oh, it's like.
Yeah, you gotta give me more than just letter D there.
1.7.
Okay, 1.7. What question number though?
D.
No, there's like question 6 or question 5, or because there's
On the review?
on the review, yeah, because in like section 1.7, I have 6 that has question 6 has a D, and question 7 has a D,
Yeah, 7.
and question 8 has a D. Question 7. So this one right here.
Yeah.
Okay, the answer key's wrong on this one, I believe. Right?
Yeah, that's
Like
fine.
super clearly wrong, right?
Yeah.
Okay.
Okay.
Yeah. I'm just making sure that this is the one.
Yeah.
4th hour caught this as well. I think there's a problem with C as well.
Yeah, there.
Okay. Yeah, my apologies on that. I'll update that here in a moment. Okay. So we're going to, oh boy, subtract 8 from both sides. Divide by -3. And let's just write it this way and dump a negative sign out of there. That probably makes life a little bit less complicated. You okay with what I did?
Mhm.
Okay. Other people, are we okay with what I did there? I just pushed the negative sign up into the numerator and then wrote it as a subtraction problem instead of having an extra negative floating around in the denominator. We'll square both sides. And then I will subtract 2 from both sides and divide by -5. So when we flip it and write, oops, it's G now. We got this stuff. Sure, you're welcome, Tessa. I am, but I did this one in the review packet like a dummy. So let's just do that. Actually, let's do this first. Come on now. Oh, there. This thing, copy. Drop this in here. And then this stuff. Don't go there. Shoot, I'll take you. You come over here. Ta-da! There we go. And then we'll take, oops. Do that. Do that. And do that. Okay. I'll go back and fix this one too in a minute. Somebody help me remember. I just want to get to other people's questions. Ariana, is that?
Yeah.
Yeah, okay. Good. Is that what you got anyways? Or close enough to it?
I think I was just thrown off because it was.
Yeah, you saw the log on the answer. You're like,
Yeah.
wait, how is that even going to get in there? Yeah, it's totally wrong. It's like massively totally wrong. Like it was a different question that got changed and nothing got updated. So there's just like, there's no reason a log would even come into this. It was from a totally different question, and things got changed and nothing got updated or updated wrong or whatever. I don't know. Mr. Kulik messed it up. It happens every once in a while. More than I'd like. All right, last call on questions. Okie McDokies. We're going to do section 2.1 here today, and then we'll call that our day. And whatever time is left at the end, you guys can use to kind of spend working on whatever is the highest priority thing for you. I'll put it that way. Which may be just like relaxing by 2:30 on a Tuesday or something. But all right. So in chapter 2, we're going to get into our real life building out of trigonometry. So just as a recall, way back in geometry, we worked with sine, cosine, and tangent. Right? And when we use sine, cosine, and tangent, we use that on what type of things? We use sine, cosine, and tangent on what?
Right angle triangles.
Okay, so we use them in angles from a right triangle, but we couldn't use them on the right angle. They had to be the acute angles from a right triangle. Right? That was our geometric definition for sine, cosine, and tangent, which is pretty narrow. What we're going to spend chapter 2 doing is extending that definition so that instead of being locked inside of a right triangle and restricted to angles between 0 and 90 degrees, we can take sine, cosine, and tangent of whatever we want. That's going to be what we're going to be doing. But to start with that, we're going to start talking about angles themselves, since that's what sine, cosine, and tangent operate on, right? Everybody's cool? Okay. Maybe we should say, we'll do that. So units to measure angles. What were the different units we had to measure angles from geometry? Degrees, yes, very good. Radians, we might have talked about. If you took the honors course, you probably should have, because I don't think any of you guys should have run into the honors course during COVID, right? The honors geometry didn't hit COVID year, or we're at home learning. And there's actually a third type called gradients. Now, that's not something we're going to do in any high school classroom I've heard of, but that's a thing, a way to measure an angle. It's basically like it's like using a slope. While it's practical in like an industrial setting, like an engineering setting, like a 4% slope or 4% grade of something, like that makes a lot of sense to talk about, but like, it's not for us. All right, so degrees and radians are what we're going to be using primarily in this course. What's the definition of a degree? If I was going to ask you what 1 degree should look like. It's a very small angle, sure, but like, how would I know when I've drawn a 1 degree angle? Right? Yeah, so nobody's ever really defined degrees for us. We're not going to do that here, but that's one of the weak points about that kind of a measuring system is like intuitively we kind of like know what we mean, and we know it when we see it, and we know like, you can envision in your head what like a 36 degree angle would look like relative to a 84 degree angle, right? You'd have no problem giving a picture of each of them matching the right angle up with the correct angle up with the correct measurement if it was just like a matching problem. Unless it was something stupid like a 88 degree angle and an 87 degree angle. But even then, if you could like cut out the pictures and lay them over top of each other, you can still figure it out, right? But that's kind of the weak point of degrees, right? Radians, we don't have that same problem. Radians have a very nice, neat, tight geometric definition. That's pretty cool. So we say that a central angle, that's not how you spell central, dummy. Central angle, that's better, has a measure of 1 radian if it intercepts an arc with the same length as the radius. Okay. So there's probably a couple words in here, geometry words, that maybe we're not quite familiar with anymore. Probably were at one point, but we've forgotten since then. Well, that's just splendid. Ugh. All right, so the first word is probably this central angle, right? What do we mean by a central angle? It's an angle whose vertex is located at the center of a circle. So let's say that's circle A. So that guy could be a central angle. Everybody okay with that? And pretty easy to see that, like, any angle you draw, I can turn into a central angle by just drawing a circle whose center is the vertex, right? Easy to make any angle a central angle. Everybody's cool? Okay, then it says, has a measure of 1 radian if it intercepts. What does intercept mean? Touches, crosses, intersects. Same thing, right? An arc. What's an arc? Like part of the perimeter of a circle, right? So in our case, maybe we'll say those points are B and C. Those points of intersection are B and C. So we call arc BC would be the intercepted arc. So what we'll say is then if the measure of AB, the radius, is equal to the measure of arc BC, then the measure of angle ABC is equal to 1 radian. Everybody agree with that, what the definition is saying? And since if you take any angle and you want to turn it into a central angle, you can pick the radius of your circle, right? You make that circle as big of a radius or as small of a radius as you want. Everybody agree with that? So you'd always be able to, like, match, you know, like the radius length to the arc length if you wanted to, right? By just making your stuff. Yes, Arson? Yes, of course. Okay. Another way of thinking about this is that the measure of arc BC equals 1 radius implies the measure of angle BAC is equal to 1 radian. And this way will be helpful here in a moment. Or that way of thinking about it in terms of, like, the arc length is equal to 1 radius. Okay. So we have radians, right? We have this nice tight geometric definition of radians. We have this intuitive notion of degrees. We have these 2 separate units of measurement. When we have 2 separate units of measurement, what are you going to always want? If I handed you a handful of change and I asked you how much money is this, what are you going to tell me back? Something in dollars and cents, right? You're going to convert all these nickels and dimes and quarters and pennies into a different unit, right? If I have radians and I have degrees, what am I going to want to have? A way to convert in between them, right? Just if I tell you, oh, go stand over there 36 meters away, and you're like, I don't know, or I don't know what a meter is. Or if I tell you, let's pick a different unit. If I told you go over there 6 furlongs from now, you're like, what the heck is a furlong? Can you convert that into, like, a unit of measurement that I'm familiar with? That's exactly what we want to have here, right? We want to be able to convert back and forth between degrees and radians because we're probably more comfortable with what 36 degrees is rather than, like, you know, some number of radians is. Everybody's okay with that? So we got to figure out a way to do that. Okay. So we have this notion that one radius, if the arc length is 1 radius long, then the angle measure is 1 radian, right? So we're going to use that. Along with another example. All right. So let's say we have this central angle. Let's figure out this central angle in degrees. How many degrees is that angle BAC? 180. Great. How'd you know that? Okay. Well, how else would we have known that? Assuming that it looks like half a circle, right?
Well,
Chanel?
half a circle.
Yeah, and a circle is 360, so half of 360 is 180. Absolutely. All those are good answers. You could also said it's a straight line, right? A straight line is 180 degrees also. All of those would be acceptable answers as to like how you knew that. They're all good ones. Okay? What we're going to do now is figure out how big this angle is now in radians. And once we do that, we'll have a conversion factor. So to do that, what I want to do is I want to figure out the measure for arc length BC. So how much is that? It's not a number, but what is BC here, the arc BC, relative to the circle? Half of the circumference. And how do I calculate the circumference for a circle? That's the area. It's the other one. 2 pi r. Well done. So that's pi r. So this is saying that this arc length is pi radii, right? If it's the length is pi r, that means that rate or that arc is pi radii long. Everybody agree with that? And if I know that one radius, an arc length of 1 radius gives me an angle measure of 1 radian, an arc length of pi radii will give me an arc length of pi radians. Is everybody okay with that? So I found here now that angle BAC is 180 degrees, and it's also pi radians. That is what I needed. So I know now that 180 degrees is pi radians. That's going to be my conversion factor that I can use. That's what I was looking for. Just like 1 inch is 2.54 centimeters, or that, 1 kilogram is 2.2 pounds, or 1 meter is 1,000 millimeters. It's just a conversion factor, right? It's a famous one. You should remember it. Like all those other ones I just spit out. I think a mile is 7 furlongs. If you're into horse racing, you know what a furlong is, but I don't suppose many teenagers are real interested in horse racing. Like the Kentucky Derby kind of horse racing in Michigan. Would be an obscure hobby to be having. Not that there's anything wrong with horse racing. All right, let's do a couple of quick conversion examples. Let's say I want to convert 90 degrees to radians. The way I'm going to approach this It's like a unit conversion problem. How many of us are currently in or have been in a chemistry class? Almost everybody. That's great. This is just going to be the same thing as your unit conversion from chemistry. So I'm going to start with 90 degrees. That's what I know. I need to multiply by some conversion factor to end up in radians. Since I have, let's say, degrees on top, what unit do I know needs to be in the denominator of my conversion factor? Degrees. So I'll put the 180 degrees down there, and the pi radians has to go on top. When I multiply these together, degrees cancels with degrees, and then I can reduce my fraction. 90 goes into 180 2 times. So then I can just multiply my fraction across. So I have 1 times pi radians, so that's going to be pi, and then 1 times 2 over 2. So that would be pi over 2 radians. Is that the only way I could write that? What else could I do? Yeah, I mean, sure. Chanel?
Okay, this is just a guess, but could you do half times pi?
Yeah, you could do that, but it's really this, that's now you're just arguing about what it looks like, right? What else might you do? What might be another acceptable way to answer this? How about 1.57? Right? What's the difference between these two answers? The first answer we'd call an exact answer. The second answer we'd call an approximation or rounded, and I would call it better than an estimate. An estimate usually don't use your calculator to get, but not a ridiculous answer. Which do you suppose that Mr. Kulik prefers? The exact answer? Will you have questions that ask for a rounded answer or an approximate answer? Sure, you could. You just have to read the direction, follow the direction. Okay? But there's nothing wrong with writing 1.57 radians, particularly if it's asking for an answer rounded to 2 decimal places. Unless otherwise stated, I would prefer an exact answer, but everybody's cool with that? Now, another thing with this, notice how I'm writing radian at the end of this. I'm going to stop doing that at some point, probably not today or tomorrow, but soon. How are you going to know if something's the difference between an angle in degrees and an angle in radians? Radians won't have the degree symbol. Degrees will. Everybody's okay with this? That at some point we're just going to quit writing radian at the end of angles with radians in it. We're just going to call it, put no degree symbol, and you guys are going to know that we're talking about an angle in radians. Everybody's okay with that?
Yes.
Now I'm going to not do that for a little while so you get used to it, but eventually we're just going to quit writing radian at the end there. Okay, let's do the other direction then. Okay. So let's say we have 2 pi over 5 radians, and I want to turn that into degrees. So I'm going to start with what I know. So I'm going to write that as 2 pi radians divided by 5. I need to multiply it by something to end up with degrees. Because I have radians in the numerator, what unit needs to be in my denominator?
Radians.
Radians. So we'll put pi radians down here, and then the 180 degrees on top. So radians can cancel the unit, pi's can cancel, And then 5 goes into 180 36 times. So I have 2 times 36, which is 72, over 1. So we just have 72 degrees. Everybody's okay there? Okay. Is there an approximate answer for this one? No, because it just landed on like a whole number, right? Let's say we have 1.6 radians, and I want to send that to degrees. Well, it's like the exact same setup, Mr. Kulik. I don't know why you're even bothering to do this example. I don't get it, but like, all right, go ahead and like go till your heart's content. It's like, yeah, I know it's kind of a dumb thing to do, but we're going to do it anyway. So radians cancel with radians. 1.6 times 180 is 288 over pi degrees. Now, in your history of looking at angles in degrees, have you ever seen an angle in degrees represented like that? No. Probably would not want to write it that way. What would you do? We would do the approximation. Why is the approximation here more meaningful than the approximation when the answer was in radians? Because if I tell you that it's a 91.67 degree angle, you would know intuitively what that looks like. If I tell you the angle's pi over 2, that gives you no more intuition than what it looks like than 1.57 radian, right? Either of those is equally meaningless to you, so let's give the exact answer. Here, 288 degrees over pi means nothing to you, but 91.67 sure does. Chanel?
Why didn't you just run it to 92 degrees? Why did you put 91?
I don't know, I just use 2 decimal places.
Oh, okay.
Because typically I like to give a couple. Drew?
Can I use the bathroom?
Yeah, absolutely. Alrighty. That's probably enough on converting. If I take
Thank you.
You're welcome. If I take our unit conversion, it doesn't take too much imagination to get to this new definition. So if I have a central angle, oh my goodness, central angle, and I'm going to call that angle theta, and I'm going to say that it's measured in radians. And that's in a circle with radius r. Then the length of the intercepted arc I'm going to call that length S, is r times theta. What would I have to do if I gave you theta in degrees and I wanted the arc length? Convert it into radians. And what do I use to convert theta into radians? I multiply it by pi over 180. So if my angle is given to me in degrees, I just tack that conversion factor on at the end, and it's gonna give me the same thing. All right, let's do a couple quickie examples and then be done with this idea. All right, let's say that so solve for S if R is equal to 3.8 inches and theta is 40 degrees. First thing I need to do is look at the angle and observe the unit of measurement. In this case, my unit is degrees. So I know I have to use the degrees version of my formula. Everybody happy there? Okay, now I'm just going to pop in my values. And then grind that way into my calculator. When I do that, I get about 2.65. What unit should be attached to this? Well, it's the length of an arc.
Inches.
Inches. Why inches? Yeah, it should match the unit of length in the problem, right? Everybody's cool with that? So what if we wanted this time instead solve for R if S is 18 centimeters and theta is 2.13 radians?
180 over 5.
Well, the first thing I'm going to do is observe the unit on my degrees. So I'm going to use the radian version of my equation. Everybody's cool with that? And then we'll just plug in my values. And if I divide both sides, I get that R is about 8.45 watts centimeters. Yes, sir. Is this easy? It should feel pretty easy. Okay. You ready for something a little bit more challenging? Just marginally. So find the perimeter of the sector with central angle of 1.7 radians. Cut from a circle with radius 5 centimeters. Now there's a word in here that is a geometry word that maybe we remember, maybe we don't. What word is that? Sector. What is a sector? It's part of a circle. Well, that's good. Yes, 100% there. What does it look like, though? A sector is a pizza slice. So if I want the perimeter of the sector, I'm looking for these distances. Everybody's okay there? So I'm going to give those a name. So the perimeter then would be, well, let's write it this way, the length of AB plus the length of AC plus the length of BC. Everybody cool with that? How long is AB? It's 5 centimeters. How long is AC?
1.7 radians.
Nope. Also 5, because why are they both 5? They're both radii of the same circle, right? Now, the 1.7 is this angle here, right? How do I find the length of BC? How about it's the arc of an intercepted angle, right? Just the arc length formula. S is equal to r times theta, since we're in radians. What's my unit? Centimeters. Yes, Ariane. Of course. What do you guys think? Okay? No biggie. One more example. A car has 18-inch diameter tires. If the car is traveling at 15 miles an hour, how many revolutions per second are the tires making?
What would you say
How many revolutions per second? RPS? Sure. I guess I forgot many in there, huh? Oh, excuse me, I'm so sleepy. All right. This, believe it or not, is just a big fancy unit conversion problem. So, I'm going to start with what I know. 15 miles per 1 hour. I'm going to do a bunch of unit conversions and end up in revolutions per second. Everybody's cool so far? First thing I'd notice is that I'm starting with per hours and I want to end in per second. Well, I know how to convert hours to seconds, right? I know 1 hour is 60 minutes. And then I know 1 minute is 60 seconds. So hours would cancel with hours, minutes would cancel with minutes. And now I'm in seconds, as I should be. That part was easy. But if I look now, I'm in minutes and I want to end up in revolutions. How do I go from like a linear distance like a mile into like a circular distance like a revolution? What's the conversion between linear distance and circular distance? Well, just that one revolution is equal to one circumference. Oh, okay. How do I calculate what shape is spinning here? Circle, because we're talking about tires. So the circumference is 2 pi r. And so what is the r in this case? Yeah, that's 9 is the radius, since the diameter is 18. So one revolution then is 18 pi inches. But what linear unit am I in? Miles. So I guess I'm going to have to convert miles down into inches. All right, fine. What's 1 mile is 5,280 feet. 1 foot is 12 inches. And then I know 18 pi inches is 1 revolution. So miles would cancel with miles, feet would cancel with feet, inches would cancel with inches, and I'm left with now revolutions per second. Yes! All right, all that's left for me is to grind out the multiplication here. So I'm just going to use one big fraction, because I know when I multiply fractions, I just multiply the numerator straight across and then multiply the denominator straight across. And unless it's not, I'm not going to bother with the ones because like they don't mean anything. So 15 times 5,280 times 12 divided by 60 times 60 times 18 pi. And I get about 4.67. Maybe I should do that. What do you guys think? It's not so bad, right? This is the trick. Over and over again. That's the only tricky part, is that one revolution was the same as one circumference. Right? Or that you could think about 360 degrees is 2 pi radians, right? That's the same kind of thinking. Everybody's okay with that? Yeah. All right. So, that being said, you guys should be able to do up through 24. Now, when's this going to be due?
Sunday.
Not this Sunday. Yeah, next Sunday. Because what should you be worried about doing this? Yeah, you should be worried about the test for tomorrow. Unless I was real bored, I wouldn't bother with starting this homework until I was done with the test. Maybe on Thursday, if you're like, I just haven't had quite enough math today, you could come home and start on the chapter 2 homework, but I probably wouldn't bother with starting it until I've gotten chapter 1 stuff off my plate. That's me, though. Maybe you're like, I want to know it all right now, and then I commend you for your intensity.